All right, one of the basic applications of a second derivative is to find a point of inflection. It so happens that the time of this recording, we are going through a global pandemic, which I suppose will be the stuff of history. So for posterity, I'm noting that here. But when we talk about the growth curve, cumulative growth curve of people acquiring or contracting the virus, it looks kind of like this in the United States. That is, there's a rapid exponential increase in the people getting the virus. Well, fortunately, that kind of growth curve does not last forever. There has to be a limiting point. Oftentimes that could be the total of the population. But there is what we call an inflection point. An inflection point, as I mentioned in the previous video, is a critical point where the curve used to be accelerating and then begins decelerating. So basically here we are increasing the number of new patients at an increasing rate. So every day we're adding more than the day before. And then all of a sudden we're still increasing the people getting sick here after the inflection point, but every day we're adding a little bit less than the day we did before, which will eventually, as you've heard the phrase, flatten the curve. So looking at it from a pure mathematical standpoint, it seems kind of weird why we would want a second derivative and why they would ask you to find a point of inflection. And of course, technology will do all this work for us, but as students of mathematics, we'd like to see what our ancestors did before technology, kind of like using an abacus. So here we go. Here's some abacus mathematics. If I give you a function, you should be able to use derivatives, first and second derivatives, to find coordinates of the point of inflection for the given curve. The function, or the question, seems to indicate that there is only one inflection point, and we'll see if the mathematics bears that out. So quickly, the first derivative of e to the x is e to the x, and the derivative of x squared is 2x, so we have e to the x subtract 2x as the first derivative. Differentiating that, we now have e to the x minus 2, 2 being the derivative of 2x, and therefore I have my second derivative. To find a point of inflection, we need to set the second derivative equal to 0. So doing, I see here I have e to the x minus 2 equals 0. In other words, e to the x has to equal 2, and you can just convert that into logarithmic form or take the log of both sides, whatever floats your boat. X is the natural log of 2. That is a significant point. That is when this curve begins to inflect. Remember, the natural log of 2 is going to be less than the natural log of e. The natural log of e is equal to 1. So this curve will inflect at some point prior to x equals 1. Now, it's not enough to say that just because the second derivative equals 0, you automatically have an inflection point. I'm going to go off to the side here, off on a tangent, pardon the pun. It's a calculus pun. But if we have y equals x to the fourth, the first derivative, of course, 4x cubed, and the second derivative is, drum roll, the second derivative is 12x squared. Now, it's clear from looking at the second derivative that when x equals 0, the second derivative equals 0, which might make you think, well, if the second derivative equals 0, we have inflection. Quick inspection of the graph of y equals x to the fourth, of course, is going to show something that's like a parabola on steroids, and it does in fact become stationary at 0, but does not inflect. The concavity continues to be concave up throughout the history of this. So even though the second derivative equals 0, the curve does not inflect, which is why all of that to say that all this stuff that's happening over here is enough to prove that there might be an inflection point. But I'm going to have to do a little bit more research to make sure, and it's simple enough, just like when we were finding stationary points. Sorry, I first found the coordinates. It said find the coordinates, so I took that x value, put it back into the equation to find the y value. The exact form is 2 minus the natural log of 2 squared, which can be done with a calculator, not to worry. I did analyze the natural log of 2 to be slightly less than 1, so I create a number line with that 0 second derivative value on it, and then I simply evaluate the second derivative on the left and the right-hand side. If this is the only place where the second derivative equals 0, then what happens to the concavity before and after? So if I evaluate the second derivative at 0, I get e to the 0 minus 2, which is negative 1. that means that the curve is concave down prior to landing on natural log of 2. Then I evaluate the second derivative at 1, and I discover that to be a positive number, and therefore the curve is concave up after the natural log of 2. So the concavity has in fact switched from down to up, which means we have inflected at the point natural log of 2, comma, 2 minus natural log of 2 squared. Or to the layperson, 0.693 approximately, 1.52 approximately to 3 sig figs. Now, of course, best way to do this, to check this, would be to put the function into graphing utility, and then you can graph the coordinates of the point that you found and verify that the second derivative crosses at that exact same spot. First of all, you can eyeball the inflection and show the concavity changing, but second of all, verifying that the second derivative does cross the x-axis here tells us that we do in fact have inflection. So, one more quick example. I won't talk as much here, but just to show you, if you have a fourth degree polynomial, the first derivative is cubic, the second derivative is quadratic, which means we could have potentially 2 inflection points. Quick quadratic analysis shows us that x could be plus or minus 1, and that would create the second derivative being 0. That should be obvious. And moreover, the question is, are those in fact inflection points? We're going to do a quick analysis indicating second derivative evaluated at 0 turns out to be negative 12, which is negative, which means we're concave down. And then on either side, I evaluate on either side of the negative 1 or 1, and I find some symmetry there, of course, and it shows me that they're concave up on each side. So there are 2 inflection points here because there's 2 locations where the second derivative equals 0 and the concavity switches in between. So I evaluate the function at 1 and at negative 1, and that yields my results. So all I have to do is look at these 2 coordinates, verify that the graph inflects there, and show that the second derivative crosses 0 at the same spot. Notice also the negative second derivative here and concave down in that interval. So I hope this was helpful to you. Thanks for watching and have a great day.